Study Section 15, ANOVA Two-Way Classification. Introduction. In one-way ANOVA, we divided the total variation in the sample data into two: variation among the samples due to different samples or treatment, and variation within samples due to random error. However, there might be a possibility that some of the variation left in the random error from one-way analysis of variation was not due to random error or chance, but due to some other measurable factor. In two-way analysis of variance, we are introducing another term called blocking factor to remove the undesirable accountable variation. Learning outcomes for study section 15. When you have studied this session, you should be able to explain the concept of blocking, construct ANOVA for two-way classification, text equality of several population means with block restricted samples. The concept of blocking. The term blocking refers to a block of land and thus has agricultural origin. For instance, if the aim of an experiment is to compare the effect of several different fertilizers, an experimental field may be divided into fairly small sections, often called plots. A stream flows alongside one edge of the field, so there is likely to be a natural fertility gradient sideways across the field. Plots near the stream might well be naturally more fertile than those further away. So, it is sensible to divide the field into strips running parallel to the stream, each strip having several plots in it, and to make sure that all the fertilizers are used in each strip. The results within each strip can be compared with each other, but there may be consistent differences from strip to strip. In this experiment, each strip is a block. The variability within a block would be expected to be less than that within the whole population being investigated. The block restriction is usually applied when an extraneous nuisance factor is suspected to have some influence on the observations, and observations within a block share some commonality based on the extraneous factor. If the block effects are found to be all equal, then the extraneous factor has no influence on the observations. Therefore, the observations within a column can be treated as an unrestricted sample. Generally, for C samples or treatments, columns, R blocks, rows, and number of observations N is equal to R by C. The separation of total variation in the sample data is shown below. Total variation SST is equal to variation between samples SSB or SSC plus variation between blocks SSR plus variation due to random error SSE. Steps for constructing the ANOVA. Step 1. Calculate the total variation SST is equal to. Step 2. Calculate the variation between treatment column means SSC is equal to. Step 3. Calculate the variation between blocks rows means SSR is equal to. Step 3. Calculate the variation due to random error SSE is equal to. Alternatively, SSE is equal to SST minus SSC minus SSR. Step 4. Calculate the average variations. Total degree of freedom is equal to SSC df plus SSR df plus SSC df. CR minus 1 is equal to C minus 1 plus R minus 1 plus C minus 1 in bracket, R minus 1 in bracket. When these sums of squares are divided by their associated degrees of freedom, we get the following variances or mean square terms. MSC is equal to SSC over C minus 1. MSR is equal to SSR over R minus 1. MSC is equal to SSC over C minus 1 in bracket, R minus 1 in bracket. Step 5. Compute the F statistic. The test statistic F for analysis of variance is given by F1 is equal to MSC over MSC. F2 is equal to MSR over MSE. The following shows the general arrangement of the ANOVA table for two-way analysis of variance. ANOVA summary table for two-way classification. Testing for the equality of population means. Hypothesis. Decision rule. Reject H0 if the calculated value of F1 is greater than its critical value F alpha into bracket C minus 1, C minus 1, R minus 1. Otherwise, accept H0. Testing for the equality of block effect. Hypothesis. Decision rule. Reject H0 if the calculated value of F2 is greater than its critical value F alpha into bracket R minus 1, C minus 1, R minus 1. Otherwise, accept H0. Example. An experimenter wants to study how weight gain in rats is influenced by the source of protein. There are 6 different diets called treatment as source of protein, and a total of 60 experimental rats are available for the study. Prior to the experiment, the rats are divided into B is equal to 10 homogeneous groups called blocks of size 6 based on initial body weight. That is, rats within a group of blocks have more or less the same initial body weight. Within each of the 10 blocks, 6 rats are randomly assigned one of the 6 diet treatment. The weight gain in grams after a fixed period of time is measured for each of the experimental rats as given in the following table. Weight gains of rats in 10 blocks with 6 diets. Based on the data, test whether all the 6 diets have the same effect on weight gain on an average. Solution. Total sample size is equal to R times C is equal to 10 times 6 is equal to 60. Treatment column means is equal to 79.2, 79.0, 77.9, 97.9, 80.0, 97.4. Block row means 95.667, 86.667, 91.0, 75.5, 86.5, 96.5, 64.5, 85.667, 76.0, 95.667. Grand mean is equal to 85.367. SST is equal to SSC is equal to SSR is equal to SSE is equal to MSC is equal to MSR is equal to MSE is equal to F1 is equal to F2 is equal to two-way ANOVA. F alpha into bracket C minus 1, C minus 1, R minus 1 is equal to since F1 is greater than 2.422, we reject H0. Also is equal to 2.096. Since F2 is greater than 2.096, we reject H0. The data indicates that there is sufficient reason to believe that the 6 diets have different effects on the weight gain in rats. Also, the weight gain is influenced by the initial body weight of the rats. 1. Treatment totals. 2. Block totals. 3. Grand total. 4. Treatment means. 5. Block means. 6. Grand mean. 7. Total variation. 8. Variation between treatments. 9. Variation between blocks. 10. Variation due to random errors. A. SSE is equal to B. Alternatively, SSE is equal to. This is the end of star 221. Thanks for listening.